All right, welcome to part 3 of 4.4, which is orthonormal basis and the Schmidt process. And in this video, the goal is to start talking about the Schmidt process. Remember that from part 2, we were kind of talking about the why, and the purpose is that when we were trying to solve these projection problems, an orthonormal basis simplified the calculations and the computations versus if we just had linearly independent columns and formed a matrix A. And so what we need to try and do then is it possible to take these linearly independent vectors that we're given and find and construct a set of orthonormal vectors that we can use that's a basis for that same matrix, and then we can use that to end up solving problems and make our lives a lot easier. And we use projections and all of our previous knowledge from this unit to do this. And so I have the 3 steps listed here, and these 3 steps are the Schmidt process, kind of in a paraphrased short form, which is we're starting with 3 independent vectors. Now we can do more. We can do less, but we're going to start with 3. I'm going to make sure it's still recording because Siri on the watch decided to activate. We're going to start with 3 independent vectors, A, B, and C. These are like A1, A2, A3. We're essentially going to construct a 3 by 3 orthonormal basis. So we are going to assume square here. But we can do this for any rectangular. From that, we want to construct 3 orthogonal vectors, capital A, capital B, capital C. And what we're going to find out is that we're going to project and then subtract that projection from the original vector, and that's going to give us our orthogonal vector. And then once we have the orthogonal vectors, we can divide by each of their respective magnitudes, and this will scale those orthogonal vectors to become orthonormal. And then if I take those as my columns for Q, we have our Q. And then in the next part, in the final part, because we'll end up having 4 parts to this section, we'll actually see where the Q comes in handy in terms of factorization, and then ultimately later in chapter 6 and 7, we'll kind of see some more uses for this in terms of eigenvalues and eigenvectors. But for now, I want to kind of illustrate this using the example that he gives, essentially walking through the process and then using the example that you can find in the text. So what we're going to do is we're going to start with these 3 independent vectors, A, B, and C, in particular A. And what we're going to do is assume A as my starting point, because we need a starting vector, because once I have my starting vector, then we can identify 90 degrees from that. And so we are going to accept A as my first orthogonal column for my matrix. And so we accept that one. To go through and now figure out what capital B is, we need to take our vector of B and we need to subtract the projection of B onto A, because that's what's going to enable us to find our error that's perpendicular. And so we're going to take our vector B and we're going to subtract from it ATA all over ATA times B. Sorry, I did this wrong. ATB A. Like this. I'm going to make sure it's not second guessing myself. But that's it. That's our projection right there. So we need to compute this. This will calculate our projection with our AA transpose is the projection of that vector. And then when I subtract it, this is going to find us our error. It's going to find us our perpendicular, our orthogonal vector here. Once I find B, then what I'm going to do in order to find C is we're going to take our vector C and we're going to subtract off each of the projections onto the other vectors, A and B, and this will give us the other orthogonal for the 3rd piece. Essentially constructing a similar pattern, taking, I'm going to kind of follow the format, A transpose C all over A transpose A times A minus, and then here we want it to be orthogonal to B, so B transpose C, B transpose B, B. If we had a 4th column, we would do this again, and I would subtract off from D the same thing, the projection of D onto A, and the projection of D onto B, and the projection of D onto C. Each time we're subtracting the next, the newest one, we're finding another orthogonal set, and another orthogonal vector. And notice how, like, as we walk through and we're making these constructions for step 2, each of these are orthogonal, but they're not orthonormal. And once you find A, you can go ahead and find the orthonormal by dividing by its length. But typically, especially me, and he mentions you can do it anyway as you find them or at the very end. I like to just do it at the very end. So once I find all 3 orthogonal columns, then I'm going to go through and divide them by each of their lengths to actually construct the orthonormal basis. But this is how we're constructing. Again, we're doing our projections and we're essentially finding the error as we're projecting onto each space, whether that's onto a line or onto a 2-dimensional space as we get into A and B here. And so at this point, let's take a look at an example. And so he gives 3 vectors for A, B, and C. So he gives A is the vector 1, negative 1, 0. B is the vector 2, 0, and negative 2. And then C is the vector 3, negative 3, and 3. And our goal here is to go through and we want to compute or construct 3 orthogonal vectors for this, and then from there create our orthonormal basis, but divided by their magnitude. So we're going to follow this. So essentially we have that capital A is our first independent column, so 1, negative 1, and 0. Again, you could go ahead and find its length to find the unit vector, but I'm just going to leave that as is. To calculate B, I'm going to take my lowercase vector b, 2, 0, negative 2. I want to subtract from it our projection here. So we need to do A transpose B. So I need to take this and multiply it with our matrix here. A transpose times that, so this is going to be a 1 by 1 kind of scalar. So 1 times 2, negative 1, 0, 0, so 2. So that gives me, this first part is 2 over. And then A transpose A is also going to be a scalar. And so if I take A transpose 1, negative 1, 0 with 1, negative 1, 0, I'm just doing dot product, remember. So 1 plus 1 is another 2. And then I'm multiplying that by my vector A, so 1, negative 1, 0. And so notice I'm really just doing B minus A. And when I do that, we'll get capital B, or orthogonal vector, which is 2, 1, and negative 2. There's our B. We'll double check. Looks like I messed up our math. Where is it? 2 minus 1. Okay. Boom. 1, 1, negative 2. Good old algebra. All right, so if we were to take A and dot it with B, hopefully you see that the product is 0. 1 minus 1 is 0, so that's true. So I have two vectors that are orthogonal. And so we need to find our third orthogonal vector. And we find that one by taking our third vector here and finding and subtracting off its projections onto these individual spaces by, again, taking A transpose, this time C, A transpose A times A minus B transpose C over B transpose B, B here. And if we go through and do this, our erase, I'm going to do this work on this side. Take a terrible eraser. A transpose C, so A transpose C gives me 3 plus 3, so that gives me 6. So I've got C is 3, negative 3, 3, minus 6 over. A transpose A again is 2, so we know that one already, times A, so 1, negative 1, 0. Minus B transpose C, so taking B, which is 1, 1, negative 2. If I do that here, so we're going to have 1, so 3, minus 3 is 0, negative 6, divided by B transpose B, so if I dot this with itself, so 1 plus 1 plus 4, so 6, times B, so 1, 1, negative 2. And so we need to simplify this, so and go through and kind of combine these vectors together. 6 over 2 is 3. I don't really think about that as 3 here. This will be minus 1, so plus 1 ultimately, just to help simplify our math a little bit. And again, just to double check. Yep. So we've got 3 minus 3, so that's 0 plus 1, so we got 1 as our first entry. Negative 3 plus 3 is 0, plus 1 is another 1. 3 minus 0, minus 2 is 1. So we get our third orthogonal vector, which is 1, 1, 1. Now again, these are all three orthogonal to each other because we've gone through and subtracted off the projections. We want to create an orthonormal basis that's connected to these independent columns, and so there's my really dirty paper towel. We need to divide each of these by their respective magnitudes, and then we would have constructed our matrix basis for Q. So I'm going to go ahead and express it here. We're going to have Q is, if I take my A, if I dot it with itself, remember how we got 2? Well, square root of that gives its magnitude. So that means 1 over root 2, negative 1 over root 2, and 0. That gives me my first column. B, again, when I dot this, how we got 6, the square root of 6 would be its length. So this would be 1 over root 6, 1 over root 6, and then negative 2 over root 6. And then C, our answer here, would have a magnitude of 3, really quick, really easy to see. This gives me 1 over radical 3, 1 over radical 3, 1 over radical 3. And we can check that. You'll see 1 over root 2 times 1 negative 1 times our capital A there is Q1, Q2, Q3, all matches. And we have our orthonormal basis. If I was to do Q transpose times Q, you should get the identity matrix. Because this is square, it should also be true that this is the identity matrix. Now, that's the Gram-Schmidt process, so hopefully that kind of helps and kind of explain a little bit. Pretty easy, to follow along in the book. You're not really performing this algorithm by hand. We would use computational programs, Maple, MATLAB, etc. There's another one that was on the top tip of my tongue, but I can't think of it, Python, things like that, that we could use to construct and do this for us. But again, hopefully it kind of makes more sense of the process itself. Why do we do this process? Why do we care about finding this orthonormal basis? Well, one, again, these calculations really simplify what we're doing, as well as this is actually going to uncover a new factorization. Because if we're taking that matrix A, I'm essentially turning it into Q, but they're not directly equivalent. In other words, there's something else that is multiplying with this Q that could take us back to A. The operations that we're performing, there's another factorization here. It's just like L and U when we factored back in Unit 2. And so that's what the last part of this series in 4.4 will look at, is the actual factorization where this question mark is an upper triangular matrix. And so how do we find that upper triangular? And it's actually pretty smooth.